Hi, this is Engineering 255, Engineering Statics. We are going to talk about the Chapter 3. This is the second video about the Chapter 3. In the previous video, we talked about basic idea. If you have several forces and acting on a particle, we can use the equilibrium equation to solve the problem in two-dimension cases. We're going to extend this idea to the three-dimension cases. So this video will focus on 3.4 three-dimensional force systems. The objectives of this video is to show you how to draw a 3D body diagram. So you are going to extend from 2D into a three-dimensional free body diagram. The basic idea is about the same, except that you have additional dimension you have to be careful about. And how do we solve the problem with three scalar equations? Because you have additional dimension, the two equations will become three equations, and how do you use that to solve the problem? The basic idea is still about the same. You just have to be careful when you do the three-dimensional. It's a little bit complicated. Let's look at some of the examples, then you will get an idea. So to give you an application cases to kind of show you why do we need this. In the real situation, again, most of the cases are three-dimensional. In this picture that we show you, there are two bars with a cable connect with a load that going down to this, probably just a pool of water, and you can see all this number that they give you are kind of tell you the dimension. And if you look at the picture, you can kind of see there's three axes. There's X and there's Y on the right and there's a Z on the top. And this red bar A and B, and this red bar B and C, and the cable D to B, and there's a cable from the B going down to the load. So each one of this is going to have a force, and how do we analyze these forces such that we can design the material to support this situation. The most important part for this kind of question is that you have to be careful to write down the coordinate for each one of the point in this example here and select the proper origin such that you can find the distance of each one of the point. Let's start with the equation of the equilibrium in the three-dimensional way. In previously, we only have X and Y, and we are looking at the equilibrium. The condition for the equilibrium is the net force has to be equal to 0. So the summation of the force vector has to be equal to 0. And we are adding the K coordinate, which is the Z direction, instead of just I and J. So you will have three equations. So each one of the equation is actually coming from the summation of F. So you have one equation of this, you have another equation for this part, you have another equation for this part. Since you have three equations, you can solve the most of three unknowns. You make each one of the net force equal to 0, and this is what we call the equilibrium equations. Again, when you write those equations, make sure that you define where is your positive direction. For example, if this is an X, let's just draw an example of the axis. So this will be my axis, and let me just say this is my X, this is my Y, and this is my Z. then I'll probably say, well, this is the x direction, which is my positive direction. My y will be in this direction, which is positive, and my z is going up to be my positive direction. And each one of this equation is a scalar equation, so you solve all the three to find the three unknowns. Let's look at an example to show you how we apply this idea to solve a real problem here. So over here you are given 4 forces, okay, and it's going to give you the geometry of these 4 forces. And we want to find out what is the tension in the cables of AB, AC, and AD. So here is our picture. We have cable here, and here, and here. So AB and AD and AC. The other force is given because we can only solve out the 3 unknowns, so one of the force has to be given, or you can find the force from the other information. Here you are given with 300 pounds. Notice our coordinate system. We have x at here, y at here, and z at here. And I give you the angle, so be careful about the angle. Make sure that you understand with those information, how do you write the coordinate points, which means what is the position for each one of this hook, okay? And that's important. Now to draw the free body diagram is going to be the first step. In this case, it's very, very easy because it kind of already tells you what are the forces, and we are analyzing the point A. So you focus on point A. And when we cut this cable, we know we are going to have a tension force along this cable. Force will be along the same direction as this cable. And we cut this one here, we also got another tension force along this cable at here. And same thing, we cut this one here, we got another cable tension force on this direction. And then you just write down the cable forces and in a Cartesian vector form. So how do you write these 3 cable forces in a Cartesian form? Okay, if you think about the chapter 2 that we talk about, how do you write a force along a direction? You need to find the position factor. So this one requires you to find a position factor. Position vector. With the position vector, you can find the unit of the position vector, the unit vector of the position vector. And this will give you the direction of your cable forces. Once you represent each one of the cable force in the vector form, then you can use the equilibrium equation by summing all the components at the same direction, make it equal to 0, then you can solve it. Let's look at the detail of how we solve this problem. So now let's look at how we can solve this problem and represent each one of the force in the 3-dimensional way. We're going to start with T sub B. If you look at T sub B here, it's right on the x-axis. So it only have the I component. And that's why we write T sub B vector is going to be the T sub B amplitude times I. And there's no Y and Z component. Then let's look at the T sub C. Now T sub C has 3 different components. One is going to be the X. So here is your T sub C at X. This part here is going to be your T sub C at Y, and this high here is going to be your T sub C at Z. Let's look at T sub C of Z. That's more easy because if we know the amount of the T sub C here, which is the hypotenuse of a triangle, that triangle is the triangle of this one here to this one here to this one here. And this opposite side to the 60 degree is our TC of Z. That is equal to T sub C multiplied with the sine of 60 degrees. So you can see T sub C times sine 60 degree is your Z component, and that's K. What about X and Y? Well, in order to find those two components, I need to find what is the length of this one here, because the length of that is going to give me the information of the hypotenuse of this one here, and these two are perpendicular because this one is our negative X, this one is our positive Y. So I can find out the X component and Y component by using this triangle, and this is a 30 degree. So what is the amount of this one? This one is the adjacent side of the 60 degree based on this triangle that we just saw. So this part here is the T sub C times the cosine 60 degree. And the component of this part is going to be multiplied with the sine 30 degree. Whatever the hypotenuse that we multiply with sine 30 degree is going to be this side here. And this part here is going to be multiplied with a cosine 30 degree. So if we wanted to find out the X component, which is negative, you use minus TC cosine 60 times sine 30, which is exactly equal to this one that we show it here. Similarly, you can find the Y component, which is the hypotenuse, the TC cosine 60 degree times cosine 30 degree. And you do the multiplication, you can simplify T sub C in this way. So that's how we find the T sub C. Let's look at the T sub D. This part is a little bit difficult. Let me just clean up the screen first, and then we'll look at that one. So first of all, we are going to look at the Z direction and the Y direction of this component first. That's the easiest part to resolve. And to figure that part out, I'm going to try to find a triangle to show you what that is. So this is the triangle we are trying to use, or actually even without a triangle, you can kind of tell this vector has a direction, has an angle between this force and the z-axis with a 45 degree. So if I multiply the cosine of 45 degree, I can find it's a z component. So T sub D at a z is going to be equal to T sub D times the cosine 45 degree. And it's going up, so this is going to be a positive. Similarly, this one has a 60 degree with the negative y direction. So T sub D with a y is going to be a negative because it's on the negative y direction. And T sub D times cosine 60 degree. And then you can find the D and the y direction. And that's how you get these two here. So this is a 45 degree, which is exactly the same as this one here. Now, this one is going to be the same as this one. Okay, it's cosine 120 is going to be equal to negative cosine 60 degree. Now, the reason that they use this one is because if you look at the x component, okay, it looks like the x component is this much, like you projecting this one down to here. However, that is not the situation, because if you look at the angle of this force, I have to clean up this one again. Look at this angle. This angle is 120. If you make them perpendicular, it's 90 degree. How can you make it 120? This force has to be behind this plane here. So if you look at this plane, this TD is actually goes into this plane. So that's how you get 120 degree. So it's actually in the negative x direction. And how much negative direction? You can simply use T sub D times cosine 120 degree to get that. Or you can think about this is in the negative x direction with a 30 degree. Then you multiply that, you will get a component. So this is really the part which is hard to visualize it, but I hope that you can understand after our explanation. So then you can represent T sub D in terms of vector form, which is this. And finally, we have a load, which is the weight here with the 300 pounds. And it's a negative z direction, so it's a k. Okay, it's a negative 300 pounds in a k direction. So now we are ready to use the equilibrium equation. The equilibrium equation tells us the net force equal to 0, and the net force including the force of B, including the force of C, including the force of D, and also the load, which is negative 300K. TB, TC, and TD are the unknown that we try to solve. When we represent the equation in terms of the x and y and z direction, you got these three equations. And I will let you to do the math, and you have three unknown, you have three equations, you solve these three equations, these three unknowns. So I strongly recommend that you practice how to solve these kind of equations. So in the statics, you probably the most situation is going to be three equations solving for three unknown, and you should be able to do it. You can eliminate one of the unknown, so by subtract two of them, such that you can get two unknown by taking two equation as a pair to eliminate one of the unknown. Then you can solve two unknown with two equations. Then you plug it in to any of this equation to find the third unknown. Okay, so this is the final solution. I'm gonna skip from here. Here is another example just to show you what we did before. This is the situation. You also have four different forces. So you have a connecting point at A. We're going to use this one as the particle point. It has a 600 Newton going down. You have three cable connect to B, C, and D, right? And they give you a dimension, 30 degree here. This one it doesn't give you a dimension, but it gives you like a distance. There's two here represent in the y direction. This point here is a y direction here. This high here is 2, and this x here is 1. Okay, so we still need to know how to represent the force in the Cartesian. That is going to be the key things that you need to know how to solve the problem. Let's look at how we get those forces in terms of vector form. We simplify from this one to this one here, and simply just try to write down the most important information and also the unknown force that we try to solve. We isolate the A point, cut off the cable, represent those as a tension force of B, C, and D. We have the weight going down here. This one is simple to represent. This is just going to the negative Z direction, so it's a negative 600 K. So this is a 600 of K. What about the B? Well, the B is on the X and Y plane, so there's no Z component. So when you represent f of B, you just have f of B times sine 30 degree is this part here. That will give you the X component, right? This is the X component. Cosine of that is going to give you the Y component, which is this one at here. That's how we get f of B. Very easy. What about f of C? Now go back to here. F of C is actually along the x direction, but it's going to be negative x. So f of C is, this is the x direction, this is a negative x direction. So this f of C is negative f of C times I Newton. Okay, now what about f of D? The easiest way to find the f of D in the vector form is to use the position vector. So we are looking at from A, go to this point, which is the D point, and you can write R from A to D. So what is the coordinate of A point? Let's make the A as the origin. And now we need to represent what is the coordinate of the D. Okay, so this A to D is from D minus A. So what is the coordinate of the D? The coordinate of the D has x to be 1 meter from the origin, and it's going to the positive x. So this is a 1 times I. The y component is going to be 2 meters, but it's going to be in the negative 2 because this y here is go to this direction. So it's going to be minus 2 of j. And for the z direction is going to be going up of 2 meters, so this is going to be positive 2 of k. And you use this one to minus the position at A, which is a 0, I, 0, J, and the 0, K. Right? And therefore, your R position vector is going to be just this one here. And we can find the unit vector of R AD by using RAD vector, this should be a vector, divide by the magnitude of the RAD. How do we find the magnitude? This magnitude is going to be equal to square root of 1 square plus minus 2 square plus 2 square, and that is what this RAD magnitude is. So what I was doing is simply just this one that shows to you, if you multiply with the amount of f of d, this is going to be the position unit vector, and you can represent f of d in terms of Cartesian coordinate. And that is the reason why we introduced the position vector in the previous chapter. Once you be able to represent that, the rest of the thing is simply just solve the systems of equation, going through some of the linear algebra part, and you solve the unknown, which is B and C and D. And here is the solution. So I hope this video that you understand how to represent three-dimensional forces using the idea of the position vector, or looking at the trigonometry. You have to use some of the imagination to think about the coordinate, think about the position, think about how this force oriented, so you can solve this problem. This is the end of our chapter 3.